Hello, Maurice, and hello, Ivan. How are you doing?
Oh, hello. Hello,
Oh,
hello, guys. Yeah, that's my great pleasure to be here for the second time to be a quote expert. Well, because when you sitting next to Morris, it's kind of hard to be expert. But still, that's my greatest honor to be here and meet and greet Morris. Morris, how are you?
I'm
You
very
you
well,
ready?
thank you.
Yeah, great. So it's very nice to see you. For Alex, help me up for the first time, for the
Third,
fourth,
third
right?
time, third time.
Third time on Hydra, and fourth time in general because we had SP this the school, right?
SPDCC. I think the first name of the school was SPDCC. So after that, we
Yeah,
add distributed. Piotr adds added distributed. So it's now SPTDC. Yes, it's fourth time we have Morris.
amazing,
That's amazing.
amazing.
Absolutely.
Yeah. So, guys, if you don't know who the Morris is, so please just close your browser. Oh, I'm sorry. That's kidding. But I hope you do really want to know about him. But because that man really changed the world. I mean, there are. A lot of regards, and to be honest, I really fail to remember all of them. But the main are uh, probably a lot of attendees knows that he is the father of all weight-free algorithm, weight-free family algorithms, because he got a Dexter Prize for weight-free synchronization. He also has a Dexter Prize for hardware transaction memory, and he made a greatest talk last year. And of course, he is author of Art of Multiprocessor Programming. That's kind of a bible for all who made the concurrency. Alex, you had a question about the second
Yes. So
edition,
because
right?
I'm a owner of paperback, so I have a princess copy. But I just like open it, show the some points, try to compare like the some items from the compare like set of chapters or things like that. And my question is very simple, Maurice. What is the difference between the first edition revised reprints and the second edition?
Oh, there are several differences. The talk that I'm giving today is actually half of a chapter in the new book. So this is a kind of a sneaky advertisement for the new material. We also extended our material to encompass C++ and some other languages, so it's not entirely based on Java. We talk a little bit more about memory reclamation. So memory reclamation is easy in a garbage collected language, but not so easy in a language like C++, when you have highly concurrent data structures. And we modernized a number of sections. We took out older things and replaced them with newer, shinier things.
Okay, thank you very much. One more thing from my side. Could you please like move yourself closer to microphone or move microphone a bit closer to your mouth? That's yes. Thanks
There.
a lot.
Is that better?
Yeah, it's much better. Thank you very much. That's it from
Okay.
my
It's
side,
way
Ivan. Yeah.
it's a way better. So despite for all that great thing that Morris has done, I think the most important that he keeps sharing his huge knowledge with everyone, and he is a professor in. Morris, could you help me to pronounce your university correct?
Well, Brown University.
Yeah, Brown University. Thanks. Yeah, I have uh, difficulties. Um, so he taught 1,000 great engineers, and today we're lucky to listen another bit of the wisdom from Morris. And so, if once again, if you haven't seen the previous talks, I really encourage you to to watch and catch up, because I promise you will enjoy it no less than a lot of the Ring or Marvel movies. So Maurice, I think we are ready to listen that wisdom from you. And
Yeah.
Okay.
Ladies and gentlemen, Dr. Maurice Herlihy.
But thank you for that flattering introduction. So, as I mentioned, what I'm going to talk about today is part of a chapter in the newest edition of my textbook. This is different in many ways from some of the other chapters. Elsewhere, we talk about fine grained concurrency, concurrent data structures. And here, for the first time, we're talking about parallel applications, how to build a larger scale concurrent applications. Now, the first thing, let me ask you a question. You know that people use the word multicore in English to talk about a processor, a chip that has multiple processors on the same piece of silicon. Now, when I was in graduate school, uh, this word was never used. People talked about multiprocessors. There were a number of other words. So I became curious, when does multicore become popular? The definition is fairly straightforward. A multicore processor is a single computing component with two or more independent actual central processing units, et cetera, et cetera. So we all know what it means, but where did it come from? So Google has a service called Ngram. So Google likes to digitize books. And when they digitize books, they keep track of words. So you can open Google Ngram, you can type in a word or a phrase, and you can see how often it is used in published works uh, in English. So this is the use of the word multicore in books by publication year. So as you can see, the frequency of the use of the word multicore goes way up after the year 2000. Uh, this is for obvious reasons because that's when people started making multicore chips. But it's curiously, in the 20th century, there were peaks where the word multicore became frequent, then it died out, then it became more frequent. And so it turns out that there are things called multicore cable, multicore fiber, lots of other uses of multicore, which I thought was interesting because I didn't know about that. Uh, but this is not actually a talk about frequency of vocabulary in published books. Uh, let's ask the question, let's say we want to implement something like Google Ngram, and I want to take a document and I want to count the occurrences of each word. So here, this document mentions the word alpha 8 times, the word bravo 3 times, Charlie 9 times. And this is a trivial program to do sequentially. Every beginning programmers class, you can ask your students to write a word count program, and they will probably do it more or less correctly. But what about if we want to do that in parallel? How would you take a problem like word count and break it up into parallel pieces? So we're going to look at a pattern called Mapreduce. This is a famous notion. You have to be careful because when people talk about Mapreduce, they talk about more than one thing. So you need to know what kind of Mapreduce they're talking about. Here we are going to talk about a very simple, abstract form of Mapreduce and then get more complicated. So the first step in doing a parallel word count is we'll take the document and we'll break it up into chapters. So I'll divide the document into K approximately same size pieces. And for reasons that will become clear, I'm going to split this among what I'm going to call the mapping threads. So each mapping thread will count the words in one particular chapter. Oh, I'm going to use this little picture of a computer chip to represent a thread. So the red thread is counting the words in chapter 1, the blue thread is counting the words in chapter 2, and the green thread is counting the words in chapter 3. Now you can see, I think, that this is highly parallel. You can see that there's not much need for synchronization. We don't need locks, we don't need barriers, we don't need any of the wonderful things that we work on in the rest of the book. This is a kind of a different flavor of concurrency and synchronization. So we have one mapping thread per chapter. So what the mapping thread does is it sequentially goes through the chapter. It builds up a list of word count frequencies. So here there's the first word shows up 9 times, the second word shows up 2 times, the third word is unique, and so on. And so each mapper thread produces a stream. So as it goes along, it pushes a stream of key value pairs. So almost everything in this talk is going to be structured as a stream of key valued pairs. This is attractive because it is clear. The distinction between parallel and sequential is clear. If it's the same stream, then it's sequential. If it's different streams, it's parallel. And we don't need to worry about fine-grained synchronization. So the key here is the word. The value is the count of the word, how many times that word appears. This will be a positive integer. Suppose we want to write this in Java or a Java-like language. We can define an abstract mapper class. This is the superclass of any thread that wants to be a mapper. So it's parameterized by a type, which is the input. In this case, this will be the document fragment. It's parameterized by a type K, which is the key. In this case, it would just be a word. And a value, which would be the integer count of the number of times the word appears. The task runs in parallel with other tasks. So unlike in a distributed system where mappers might be separate machines, here each core is going to be a mapper. So we're going to have mapper cores, or actually mapper threads, to be more precise. So this is a combination of fine-grained threading with the Mapreduce pattern. So all of the mapper threads run in parallel with each other. And this is what's called embarrassingly parallel because there's no need for them to synchronize with each other because they're working on separate pieces of the document. Now, what the mapper produces is a map data structure. I know the terminology is confusing because everything is a map, but here you can think of this as a table or a database, mapping each key to its value, each word to its count. We'll provide a simple method that sets the input. So this would be the name of the file name of the chapter that you're working on. The word count mapper. So that's an abstract mapper. We're going to use that for anything that acts like a mapper. And later on, we will talk a little bit about what mappers look like. So here we have a word count mapper that exists precisely to count the words in the document. We're going to instantiate the input as a list of strings. So before we create the word count mapper, we're going to open the file and parse it and break it up into a list of strings. What it returns is it's going to be a map that takes each string, that is each word in the document, mapped onto the account. And we'll make this a long integer because maybe our document is very big. here is the word count mapper in more detail. So the compute method does all the work. So this is a method that is inherited from the thread class, from the recursive thread class. And the convention is that the compute does the thread's work. So the first thing I'm going to do is I'm going to create a map to hold the results of the mapper. So I'm creating a new hash map that goes from strings to longs. This is a variable declaration, a new statement that creates an empty map. And then I'm going to go over the entire input, one word at a time. And I'm going to increment the count associated with this word. This is a never is Java 8 and later functional syntax. The details don't much matter. When we finish scanning through the entire document and returning the and we've populated the map with all of the key value pairs, then we return the map object as a result of the computation.
Hi, Maurice. Seems like we have technical difficulties with the slides. Seems like we can't show it to the audience. So, hey guys, which slide did we stop? Yeah. Do so if you hear. Would be nice if you tell us where did we stop. Okay, yeah, but that's a nice introduction. Morris, actually, I had a question about, you said that Mapreduce usually has many definitions. So now we just counting like a classic Mapreduce. We split like splitting conquer, right? Divide and conquer. Sorry. Yeah, but what the others? I mean, I can.
I was thinking more of the differences between Hadoop and Spark and Google's Mapreduce. They all provide somewhat different functionality. At the end of the talk, I'll talk about distributed Mapreduce, which
Uh,
is different in many ways from a multicore Mapreduce. So
ah,
if you're running Google search, then you probably don't want to run on a multicore. But if you're running if you're doing machine learning on your laptop, then a multi-core MapReduce would make more sense. So the scalability is different, the fault tolerance is different, the kinds of problems that are appropriate are somewhat different.
I see. But can we combine both approaches? Or probably they are combining.
Yes, I think you can certainly combine these. And again, the question is, what's the most appropriate tool for the kind of thing that you're trying to do? If you're trying to run Google, then you shouldn't be worrying probably that much about multicores. But if you're trying to do machine learning in a small business with a small budget, then using a multicore is probably more sensible.
Ah, okay. But I thought they kind of out the box. If we have one box, we can try to get as much as we can from that box. If we have two boxes, we try to uh, get as much as we can from two boxes, and this
Yes,
is
yes,
hopefully.
and I think traditional MapReduce tends not to focus much on multi-threading. They use coarse-grained concurrency, and so I think a combination of the multi-threaded MapReduce and distributed MapReduce would be ideal. I don't know if anyone is currently doing that.
Oh, okay, I see. Okay, seems like these slides are bug. Yeah, sorry everyone for these technical difficulties. We are at the moment when we merge, when we compute, we do the thing with the word, and we merge that word into the result.
Yes, exactly. So here we increment the counter, and I was apologizing for the syntax because this is advanced Java syntax, but it fits on the slide. Then when we're done, we return the map. So this is what the reduce phase looks like. So the mapper, remember, goes through and it picks one chapter of the document. Then it counts the words there, and then it sends its stream of results, its table of results, to the reduce thread. There's only one reduce thread, and the reduce thread merges them. Now, this is a deliberately chosen to be an almost trivial example of an application because I want to make sure that the overall structure is clear before we talk about more advanced applications. So I'm hoping that this makes the principles clear in what happens. So the reducer thread merges the mapper outputs. So clearly the nature of the problem has to be such that the work can be split among the mappers, and there is a way to merge the results of the mappers to get back the final answer that we want, which for word count is fairly obvious. The reduce phase uh, outputs a table with the final word count, with the word count for the entire document. And so it produces a stream. We're going to be using streams and maps uh, pretty much synonymously. But everything is still a key value pair. So the key here is still a word. The value is the global count, the count in the entire document. So the keys and the values at all levels are the same in this example, although they will be different later on. So this is what the reducer class looks like in Java. Again, this is the abstract reducer class that is the superclass of all reducer classes. It's very abstract. So it's given a single key and a list of associated values. So these are factored slightly differently than the mapper. Here, each reducer gets a key and a stream of values. It produces a single output value, which in this case would be the total count for that word. Now, let's look at a more advanced application, something that you might want to do in a machine learning application. So we can take the word count for a document and we can normalize it. That is, we can divide it by the total number so that we end up with a vector whose sum, where all the entries sum up to 1. So this tells you the frequency of the words, but not the count. So this says you can tell which are the most common words in the document. And you can view this as a fingerprint. So a normalized word count is a point in a high dimensional space that tells you something about the document. The frequency of words can give you a hint as to the meaning of the document. What is the document about? And people who work on data science know that documents on similar subjects tend to cluster together. So if your documents are documents that contain Russian poetry, are probably going to have different fingerprints than documents that have Argentine tango song lyrics. And both of them are going to be different from computer science technical papers. The shared vocabulary in each of them is probably fairly small. So this introduces another problem called k-means. Suppose we have fingerprints for a large number of documents, and we suspect that these documents are about a small number of subjects. So we want to cluster the documents. I want to try to guess which ones are technical papers and which ones are poetry and which ones are song lyrics. So what I want, definition of a cluster is that I want to divide them so that each vector is closer to the vectors in its own cluster than it is the vectors in different clusters. I want to be able to look at these points and say, these are clustered together, these others are clustered together, and there is no, it is highly unlikely that something that is, you know, far away from the other technical papers is itself a technical paper. So let's do clustering here. So what I'm going to do is I'm going to randomly split the points among the mapping threads. So remember, we have a collection of concurrent mapping threads. I'm going to randomly give each one an equal number of points to work on. And each reducer is now going to try to cluster its own little bag of points. So it's going to start out by randomly picking case centers. So it has no idea where the real center is, so it's going to start by just making a guess. So it randomly picks case centers from the collection of points. And what it's going to do is it's going to send each of those centers it's going to send that vector of centers to the threads, to the mapping threads. So the mappers are going to try to cluster each of their own points around the centers. So the reducer sends key value pairs to mappers. The key is a cluster number, and the value is the central point, or the guess at the central point. So I'm going to say, here is cluster number 1 is centered around this point, cluster number 2 is centered around a different point, and so on. And so what the mappers are going to do is the mappers are going to use the centers to assign each vector to a cluster. Now, as you can guess, this might be highly imperfect, depending on the quality of the centers. So it says, okay, point 0 is in cluster 0, point 1 is in cluster 1, point 2 is in cluster 2, point 3 is in cluster 0 again, and so on. And in this way, it's going to assign each point to a particular cluster based on its local information. And this can also clearly be done in parallel. So the benefit of doing things this way is each mapper can work in parallel on doing its own clustering. What the mapper does is it sends a key value pair to the back to the reducer. So it maps each point to a cluster. So P0 goes to cluster 2, P1 goes to cluster 1, P2 goes to cluster 2, P3 goes to cluster 0, and so on. So the key in the key value stream are points. The values in the key value stream are cluster IDs. So the centers go down and then the assignments go up. So what does the reducer do? The reducer merges all of these streams. And so it says, okay, so everyone thinks that this cluster is cluster 0, this cluster is cluster 1, and so on. So now the reducer has divided the points into k clusters, kind of roughly. So at this point, the reducer has a kind of a classification. Now what the reducer does is it throws out the old centers and says, well, those centers were chosen at random, and I had no idea what was going on there. Now I have a rough, crude notion of clustering. I'm going to pick new centers. using some technique, a Barry center or something like that, a median point. So now the reducer chooses new centers, and then it starts over again. So then it creates the new centers, it sends the new centers to the threads. Those threads cluster their points around the new centers. And this may change the assignment of points to clusters. And the reducer sends the new centers to the mappers. And this continues until the process becomes stable. At some point, every mapper will leave its points in the same cluster where it was before. And at that point, you have a good clustering. And so this is, a highly parallel clustering uh, algorithm called k-means, which is very popular among people who do machine learning. It's non-deterministic in the sense that the results may depend on your initial choice of centers. So if you run it twice, you may get slightly different results, but it's very parallel, very efficient, and it's considered quite good in practice. Now, the point that I'm leading up to here is not to teach you how to do clustering. The point is to get you to think about the parallel structures of problems. So that at an abstract level, the parallel structure of k-means is similar to the parallel structure of the word count, even though it's more complicated, and even though k-means is iterated. Word count you do once. K-means you iterate until it converges. But this idea that you can break things into mapping threads and into a single reducer thread is the key point that I want to emphasize here. So to recapitulate, so we saw two problems, word count and k-means, which are superficially might seem quite different, but the underlying abstract structure is exactly the same. This is why we can inherit from the same Java classes when we implement them. And the parallel solutions are basically the same. So this is an important pattern. So when you're faced with a problem and you want to know if you can parallelize it, one way to do this is to say, can I consider this as a Mapreduce problem? Some problems you can do this, other problems you can't. Sometimes, if you're clever enough, you can take a problem that does not look like a Mapreduce problem and turn it into a Mapreduce problem. So this might be a good time to pause and see if there are any questions.
Well, I think more or less clear. I don't see a lot of questions. Paulina asked about can you have multicore Mapreduce inside distributive one? But I think we can address that question. But we can conclude that yes, you do, but seems like it's not much tools are really doing that at the moment. Correct?
Correct, yes.
Okay. Yeah, thanks. We can move on.
Okay, we can proceed. So again, the main part is that the map part is parallel and the reduce part is sequential. So this is kind of what the way to think about this, that the map parts in some sense provide the power. They do all the work, and the reduce thread in some sense directs everything and controls everything that happens. So the map part is parallel, does all the work. The reduce part is sequential, and it basically directs what the map does, and it turns the work generated by the mapping threads into something useful. So we can, what kinds of problems can be expressed effectively as map reduce problems? Well, the map function is something that takes a stream of key value pairs as input, and it produces a stream of potentially different key value pairs on the way out. So if you can write your parallel thread in this form, that it takes in a stream of key value pairs and produces a list of key value pairs. And in the word count case, it's the document and the contents. So the key is less important than the contents here. And the output is a list of words and their counts. So the key value or the word count actually fits this pattern. The k-means takes the cluster ID and the center, and it comes back with a mapping from points to cluster ID. So again, even though that these look superficially different at an abstract level, they're very similar. And when you write the software to do one or the other, you end up inheriting from the same classes and writing a very similar code, mostly just changing the types of the objects. The reduce function takes in keys and key and list of value, and it returns a stream full of a list of values. So in our example, in word count, this receives a stream consisting of words and a list of counts, one from each mapper. And what it returns is the list of counts. So each word comes in with a list of counts, and it merges with a single count. For k-means, what comes in is a cluster ID and list of points, and what comes out is a new center. So this is designed so that we can iterate this process. But here too, if you describe the problem in an end-to-end way, they look very different. But if you look at the underlying structure, they're quite similar. But there are many other things that you can do in a Mapreduce style pattern that may seem that again look very different from the examples that we've seen, but at the lower or at the more abstract level are very similar. So you could have a distributed grep that is pattern matching. So the mappers might say take in a line of document. So the mapper reads in a line of document, it searches for the string that you're looking for, and if it finds it, it sends it back to the reducing thread, to the reducer thread, and the reducer thread just copies the line to the display. So this is an example where the computations themselves are fairly trivial. It's the overall structure that's important. And the more you can make the mapping computation trivial and the more you can make the reduced computation trivial, the better off you are, because that means you have more seamless parallelism. Another example is you might ask about the frequency with which a particular URL is accessed. This is something that people who collect web statistics do all the time. So what the mapper does, the mapper takes a URL and a local count of the number of times it was accessed. So this is an application where you have a page that has URLs embedded in it, and you want to know how often do people click on it. And so for each page on a website, a mapper might keep track of the URL and the local count, and the reducer simply takes the local counts and puts them together. So this is similar to word count in a number of ways. It's also run iteratively, so it can update its statistics each time. So this is, again, the kind of pattern that would fit a Mapreduce pattern. Reverse web link graph. Who is linking to your page? Uh, the mappers will walk through the web and look for target link and source page So each mapper will produce a stream of target links and source page, and the reducer will basically concatenate the source pages and say, well, here's a target link, and here are all the pages that point to it. So this is kind of a reverse search. So this is the most natural way to address that kind of question. There's lots of other examples that you can think about while I'm talking. One is a histogram. So imagine that I have a big, I have a file full of numbers, and I want to look at the distributions of those numbers. A natural way to do this is to uh, the same way we did with word count is you take the file, you divide it into pieces, you create a map thread for each piece. Each piece creates its own local histogram sequentially, and then the reduce thread takes all of the histograms produced in parallel and merges them. And again, this works because the histograms are the kinds of things that can be merged. A lot of matrix operations, interestingly, can be done using a Mapreduce. So you can do a row and a column manipulation with map threads, with mapping threads, and combine them with the reduce thread. And it can be a fun homework problem or exercise to say, here are some standard matrix multiplications, including multiplication, addition, determinant, and so on. Can you structure those as MapReduce problems? Can you get a better concurrency that way than you could by explicitly, creating threads and having threads communicate by synchronized queues and other kinds of more mainstream multicore mechanisms. The famous PageRank algorithm, the one that started off of Google, that's a distributed graph algorithm. And PageRank lends itself very well to MapReduce. In fact, MapReduce was originally invented at Google to efficiently compute PageRank, which was also invented at Google. So this a lot of this originated in Google. It's been enthusiastically adopted by other groups and other software producers. I don't think you can actually use Google's implementation of PageRank, but there are many open source implementations of MapReduce, uh, at least in distributed MapReduce that you can use. There are lots of measures. Betweenness centrality basically says if you have a social network graph, who's the most important person in the graph, in the sense that they're closest to everyone in the graph. This is given the unlikely name of betweenness centrality. The exact definition is not so important, but there are a family of statistical measures that can be computed in parallel on very large graphs using this MapReduce pattern. So again, MapReduce is not going to solve all of your concurrency problems. There are lots of things that will require more traditional locks and threads and so on. But it's very powerful for certain restricted applications. So someone earlier asked about the difference between the kind of MapReduce that I'm describing here, which is multi-threaded MapReduce and distributed MapReduce. So this is a picture from one of the early distributed MapReduce papers. And this describes, I think it's the way either Google or someone like that does MapReduce. And you can see that these are, at a kind of an abstract level, it's similar, but the systems aspects are very different. So for one thing, all of the communication goes through files. So Google, the mapping workers and the reducing workers communicate by going through the Google file system. whereas in a shared memory, they can communicate directly through streams or by having threads that return data structures. So the mechanics are very different. Hadoop is an open source package that if you want to do scientific computation, machine learning, any of these things that can benefit from distributed Mapreduce, you can download the code. There's another, there's also a Spark, which is a Scala-based Mapreduce system. These are very popular, very powerful systems. They're not really multi-threaded as they are distributed. Your each mapper is a separate server. The reducer is a separate server. They're not lightweight threads running on a single address space. They do communication by message. In the examples that I've shown you, we do communication by passing shared objects. So the abstract pattern may be similar, but the culture is different. I'm describing something that lives in a shared memory multi-core world, not necessarily in a distributed message passing world. And the, again, which one of these you want depends on what you want to do. So one of the big differences is that if you're doing distributed MapReduce, you have to worry about fault tolerance. So when I issue a query on Google and probably on Yandex and probably on Microsoft, it probably goes to hundreds or maybe thousands of servers. And not all of those servers are going to be up at any time. So the distributed MapReduce systems have to be highly fault tolerant. So they have to be able to tolerate some number of mappers and never responding. So you would need to write your reducer to say, hey, everybody work on this for me, and I will return when I have 90% of my answers. Or I will return after 100 milliseconds, no matter how many answers I get. And this is not something that makes sense in a multicore. In a multicore, you're not worried that your threads are going to crash. I can't imagine a situation where you would want to write a multi-core application that says, "Oh, it's okay if some thread crashes. We're going to keep running," because that doesn't happen that much. And this has a very large impact on the way that you write your code and the way that you design things. So it's a very different way of thinking about things. So multi-core MapReduce, there's a number of papers. They mostly seem to be interested in machine learning applications because everyone is interested in machine learning applications. But you can also use it for very scientific and numerical applications. And what these papers do is they have to worry about different kinds of performance than the people who do distributed MapReduce. So while the mathematical principles are the same, the engineering is quite different. So one thing that's important is the way you lay out your keys and values has a big effect on cache performance. And as you probably know, the one aspect of your program that controls its efficiency is cache performance. If you have bad cache locality, your program is going to perform poorly no matter what kind of underlying algorithm you use. So you want to think carefully about how you lay out the key values in memory to keep your cache hit rate high enough. Memory allocation turns out to matter. As you can imagine, if you can do static memory allocation, if you know in advance how much memory you're going to need, then you will perform better than if you need to allocate your memory dynamically. Similar things have to do with if you're freeing memory through garbage collection or freeing memory explicitly. These can also have a big effect on your performance and throughput. And here too, this is not such a big deal in a distributed MapReduce system. The mechanism overhead matters. So when I was experimenting with the Mapreduce in Java, I started out using a different kind of thread, and the performance wasn't great. And then I replaced it with a newer, recursive thread, and the performance was much better for most of the applications that I looked at. So there's a lot of fine-grained engineering that goes into making these kinds of these kinds of systems perform well. And this kind of engineering is, again, very different from the kind of engineering you would do in a distributed system. Uh, again, because the things that control your performance are quite different. It's caches, threading, and computational overhead. Whereas in distributed map release, it's things like message latency, uh, fault tolerance, and the communication medium, whether you use a shared file system for communication or not. Okay, so I'm going to basically finish up um, here and open the floor for questions. I hope I've provoked some questions. So I want to say that MapReduce is a powerful way of thinking. I don't want to exaggerate it. It's not going to solve every problem that you have, but it can be used for some things like word count and k-means may be fairly straightforward. Other things like matrix multiplication, partial differential equations may be less obvious. The point of this whole chapter is to encourage people to think about their overall applications in this way. In the rest of the book, we tend to focus on low-level mechanisms. How do you build a lock-free data structure? When do you need to put in memory barriers? These are all engineering things that need to be addressed in order to make your programs correct and perform well. But here you need to kind of raise things to a higher level and think about the overall structure of your program. Can you write this in a form? Can you divide your task up into parallel mappers whose labor can be merged by a sequential reducer thread? If so, then this is a promising approach. If not, then you need to think about something else. Now, the truth is that the most common use for MapReduce right now is in distributed systems, not so much in the multicore. Google, the Yandex, the Microsoft search engine, they all use various forms of MapReduce very successfully. They're distributed systems. They worry about fault tolerance. They rely on shared file systems. They pretty much the things that they need to worry about are complement the kinds of things that we need to worry about in a multi-core system. And for this reason, multi-core MapReduce is not as common because it doesn't address the same kind of scalable problems. But it does make better use of your multi-core engine than a single-threaded implementation would have. And so, what I hope I've convinced you is that this pattern also works on multi-cores. It's a way to make good use of your multi-core resources. It's not that hard. It requires some high-level thought, but the actual programming, if you think about it carefully, is much simpler than, say, writing a lock-free data structure. It's much more likely to be correct. It's whether it performs well again depends on lots of programming detail, but it's probably no worse than any other kind of systems. But again, the key is to focus on the high level problem structure, which is something that we don't always do in concurrent systems. And again, unlike the other um, work that we covered, this is I think it's fun because it's in some sense the complement of the usual approach. In the usual approach, we focus on threads and we focus on fine-grained synchronization. we look at compare and swaps and lock-free synchronization, or we look at threads. And so at this point, I'd be happy to take questions.
Yeah, thanks. Thank you very much. I 100% sure over here should be a ton of uploads if we were offline. Yeah, we had a great question from Konstantin Plotnikov. It's a question about reduce. So probably reduce A B and reduce C D can be go um, separately and reduce them both. They could be also be a parallel job. So how many reducers do we have, and can we parallel reduce as well?
So we can
And do
absolutely
we need?
parallelize reduce as well. I did not talk about that because I didn't want to frighten people. So I think it's easier to describe reduce as being internally sequential. And once people are comfortable with that, then you can say exactly as the questioner observed. Well, often you can parallelize the internals of the reducer, and you can also parallelize sometimes the internals of the mapper, although that happens less frequently. So certainly there are other opportunities for parallelism. It's easier to explain things in terms of sequential processes, but by all means, if you if your application will benefit from that kind of parallelism, then you can go for it. That's also a good excuse to use the other chapters of the book.
Oh, great. Yeah, I was about to ask you about some examples where it could be where it makes sense to parallel reducer. For example, the grep distribution grep example. I think it's not really right, or like with that words counting. It's more like plus
Yeah,
and
those
without.
examples
You know?
exist to for pedagogical reasons. I mean, you might plausibly do word count that way. Grep, is pushing things a little bit. The goal there, though, is to get people to think in this particular kind of parallel way. You should ask yourself, can I structure my problem in this way, and then take it from there. The existing systems like Hadoop and Spark actually have very sophisticated and complicated controls. You can talk about how often things run and many knobs and many things that you can adjust. And talking about that wouldn't really be appropriate in a beginning lecture, but people should be aware that these things exist, and that's how people who do Mapreduce professionally, they spend a lot of time fine tuning these controls.
Okay, gotcha. So, do you encourage to try to build your own MapReduce, or probably to try first some common approaches like in Kafka, I don't know, Hadoop or something like that?
Oh, I think particularly if you're doing distributed MapReduce, it makes much more sense to use someone else's code if you can. It's I always tell my students you're better off using other people's code except when you're doing your homework, in which case that will get you into trouble. But if you're doing something for real, then you should always build on other people's work rather than writing your own code, because you know that code people have had time to find the bugs in the code. Now, if you want to do multicore MapReduce, I'm not sure what you would use. We have some demo code, but it's not engineered for serious use. It's engineered for classroom use, and so if there's a choice between clarity and performance, we go with clarity. But if you need to get work done, then you maybe want to write a code that's not quite as elegant.
Yeah, I see. But do you have any theory why? Well, that's kind of an obvious idea to combine those approaches. So yes, we have distributed Mapreduce, but obviously we have a machine which has a ton of cores, and it doesn't have all that disadvantages like a message could be lost. So the kind of obvious way to improve any Mapreduce, but according to you, it's not widely used. Do you know why?
Well, you can get some of the effect by virtualization. So if you go to one of these cloud computing companies and you do MapReduce, you're probably running on a small number of physical servers, but they've
Mm.
virtualized lots of processes. And virtualizing processes is much less efficient than running threads, as in my examples, but it's a lot easier. And so, unless you're willing to do the work of writing a fine-grained uh, threading a package, then just running virtualization will help you use the cores, even if it's not of ideal efficiency. It's the ideal amount of work, which is basically zero.
Mm. Okay, okay, I see. Um, and yeah, another question. If we change the thread to a process, would be it makes sense or not?
I would be concerned that processes are are fairly heavyweight. So the way that these Java threads work is you have long lived processes that basically they do work stealing. So
Mm.
when you give a thread, is created, it lives for a short amount of time, and then it goes away. But really, these are implemented as jobs in a queue, and you have a small number of processes that when they become idle, they pull a job off the queue. So there are processes underneath everything. The threads are, in some sense, an abstraction that exists to hide the processes, but the work is actually being done by processes. So I don't see any benefit in making those processes visible to say, to the Java code. The reentrant tasks are I think, in some sense, the ideal interface because they're lightweight and flexible, and the Java virtual machine runtime scheduler can is usually quite efficient at making use of the hardware processes.
Mm.
So I
Okay,
would stick
I
with
see.
threads.
I thought maybe some like the two problems. The first, I see that OMM killer out of memory. If we kind of out of we took on our plate much more that we can chew. There probably might something bad happened and we crashed and we have to start it over again. And another one probably some NUMA effects, but I'm not sure that processes could help with that. What do you think about it?
Yeah, I think with the memory part, I'm not quite sure. It's true. If you run out of memory, then you're probably in trouble, and that then you have to reboot your machine or something like that. So it's good to avoid that. NUMA effects. It's hard to say offhand what would work better with NUMA effects. You can. I imagine you can do things like you can you can bind a thread to a particular processor um, if you know what you're doing. So if you're willing to put in the work and the testing, you could say, well, I want to I'm creating a thread and I want to bind it to a particular hardware processor because I know the data that it is going to be using is close to that processor in the NUMA architecture.
Mhm.
But that's something that I think is very application dependent. So I don't want to suggest that all of these optimizations I think make a lot of sense, and you probably want to think about them for an individual application. I'm not going to say anything about them in the lecture because this is kind of a general lecture. So I encourage people to think hard about their particular situation and to think about what optimizations might make sense in that situation. I don't want to rule anything out.
Mm. Okay, yeah, we're definitely coming down to the level of optimization and more advanced topic. So probably that's the later chapters from your book, right?
Yes, no. So I think if the readers are worried about optimization, then I think I've done my job.
Okay. Yeah, that's a good adversity for art of multiprocessing programming. Yeah, but if just concludes what we discussed so far about the Mapreduce, I kind of think about the ideal situation when we have a distributed okay, or just several boxes that do their job, and we divide the job. And on the single machine, we also divide the job by several processors, each on its own NUMA node. That's probably would be ideal regardless of the task. Would you agree with that?
Yes, I would agree with that, and I think in some sense, it's actually an approach that lends itself well to abstraction because the distributed part doesn't need to know that there is a multi-threaded part underneath. So
Yeah.
if you can take one box that looks like a sequential mapper and implement
Mhm.
that using its own multi-threaded MapReduce, then I think you're in a good place because the two systems are in some sense isolated from each other. The multi-threaded system doesn't need to worry about interprocess communication or fault tolerance, and the distributed part doesn't need to worry about cache locality and so on. So I think that would be an ideal setup. But I think it's important to keep a layer of abstraction so that the two pieces don't start to um, depend on one another.
I see. I see. Thank you. Thanks. Yeah. Yeah. So, guys, we got a brief introduction to data science, so you can update your CV, and once you get your huge salary, you can consider to share some bit of that with Brown University.
Absolutely.
Yeah, so we can. I think that from audience, not so much questions. So guys, don't be shy to join our discussions. And furthermore, we will have a discussion zone where we can discuss the more advanced topic about map reducing. Um, yeah. Uh, Yeah, one question from me that probably not related to MapReduce itself, but yeah, once we talk about threads versus processors, can we talk a little bit about threads versus green thread or coroutines? They getting more and more popular nowadays. And what do you think in this particular case, probably MapReduce? Would be reasonable to go with that approach as well.
I think it probably would be reasonable. I haven't tried it, so I can't assert that it is either a good or bad idea, but it seems very promising. You know, you typically have a pretty good idea of how many resources you need, how many threads you're going to create. So I don't see any problem with that offhand. You know, again, I haven't explored this subject, so there may be something. There may be some terrible mistake there, but I can't think of it right now. So I would say it's probably okay.
Mm. Okay, so yeah, my understanding that advantage of the coroutines usually when you cannot um, provide for a single thread as much job as it can. Look, like the thread can do a lot of much more work than you can proceed, and So in my mind, so the task like computations where you yeah, like we just saw, you just take a word and you just put it onto the map, but still it's like a lot of memory access, and a single CPU can usually just idle, right? So probably the several threads over or even on the single CPU is a good idea.
Mhm. No, I think that makes sense because most of the examples that we've seen do involve I/O. So you're I think you're right that the processor would be idle while you're reading in the next word from the file. That made that also that harkens back to the question of things like cache locality. How often you hit in the buffer, how often you hit in your cache, and that determines how busy your processor is. So if your map, if your keys are in one place and your values are in another place, then you're going to get worse locality than if they're on the same cache line, for example.
Mhm. I see. Hey, Alex.
Hello, are you hear me? Yeah. Uh,
Yeah.
okay, thank you very, very much for the talk. And I want to say thank you very much. And again, Ivan, Maurice, this is a great honor for us to have you on board this year. And one more thing to our audience, to follow Maurice and Ivan in discussion zone, please press camera button in the right bottom corner of the player and join our Zoom discussion, because I know that it's maybe not early morning in Russia, but anyway, it's like almost 10 p.m. But I think that somebody still has some, energy to discuss concurrency with Maurice. I think it's a very unique ability for our people. Again, thank you very much. Thank you, Maurice, and thank you, Ivan. So please follow the link and go to discussions on Zoom. Bye bye.